Good morning, everybody. I'd like to thank Julian Juarez for inviting me to this event. It was very nice to see the works that you guys are doing on Tuesday. Your presentations are doing a really good work. Keep up the good work. I'm sure you're gonna continue doing some excellent research. So let me see. This is the summary of my talk. The title is Technical Details. It's a kind of broad aspect of molecular dynamics, but I'll try to focus in some aspects. So I'm just going to revisit some basic principles of classical MD. Kaline yesterday did a great job presenting the methodology, the limitations. I'm going to revisit some principles for this to help me with this discussion. I'll talk a little bit more about lamps. Julian also made a good introduction of lamps, and you guys have the tutorial. I'm gonna talk a little bit more what we can do, what we can't do on lamps, and focus on personal experience over the years in simple but important comments toward obtaining accurate and reliable results in MD. So, for example, Paul Pitts showed like dozens of potentials with many parameterizations. How do I choose a suitable potential for me? So we're going to see the availability in lamps and see how we can, for example, check the suitability of the potential by validation tests, and also some, we're going to discuss some points on convergence tests to make sure that you are taking the best that this tool can offer. So some comments from the previous days, people ask sometimes, can I trust this result? Can I believe on this potential? So we are not believers, we are scientists. So we do tests and we analyze the results and we see if they make sense or not. So that's kind of things I'm gonna talk. And again, they are usually simple to do, but people usually overlook, they don't care. They just get lamps with reacts, start doing a lot of complex simulations, they don't care about the precision, the quality of the results they are doing. And if I have time in the end, I'm gonna show some examples of applications MD by our group. Our group works with DFT-MD, focused on material science, more specifically carbon nanostructures, and some processing techniques like high pressure treatment, pyrolysis, irradiation. And I'm gonna focus in some applications in MD. So the molecular dynamics, from a mathematical point of view, is quite simple. We are solving the second law of Newton, equations of motion for classical bodies. So we can see, for example, from an initial configuration, initial position, initial velocity, we can compute the trajectories of these billiard balls on this table. And for this, we have to solve 6 equations, 6 ODEs, okay, for the position, the x, y, z coordinates, and the velocity along these 3 different directions. So mathematically, that's all about molecular dynamics. The complexity lies on the computation of these forces. So we had this talk before by Paul Pitts already showed there are many options on how to do it. Yesterday, Kaline also showed some specific force fields for biomolecules. So all the complexity, actually the heart of molecular dynamics is the accurate computation of these forces. So molecular dynamics, what we do, we treat atoms or molecules in the system as classical bodies, and we compute the time evolution of the system that we call the atomic trajectories, which allow us to observe directly the dynamics of the process. But we also can use this tool to analyze systems in equilibrium, because we can sample a sequence of different microstates within a given sample, and basically if we can compute an instantaneous property based on the position, the velocity, we can average over the time, and provided that we are exploring the phase space in an appropriate manner, like Kaline said yesterday, using, according to the ergodic hypothesis, an average time is equivalent to the average of an ensemble. So we can analyze both equilibrium and non-equilibrium processes. Here's some, Paul Pitts already mentioned in his previous talk, we can compute properties in condensed matter, understanding phenomena from a microscopic point of view that we can easily see with experiments. We can use to study new materials in process and understand more about the existing process. So this is a list of, for example, applications that we use that we do in our lab, but of course there are much more to it. And as I said, let's revisit the basic algorithm of molecular dynamics. In this first part of my talk, I'm going to talk what aspects are important on each step to guarantee an accurate simulation. And towards the end of the talk, I'm gonna go in deeper details about each one of the steps. So this is quite simple. We start with positions and velocities for atoms, and we enter in a loop where we compute forces on each atom according to an interatomic potential. We update the velocities and positions for a new time by the integration of the equations of motion. We compute desired properties, and we repeat this operation for as many time steps as needed to reach a total time of simulation, and then we can analyze and post-processing the results. So the first step is to start with initial configuration. We have to set up the positions of our atoms. That can be simple for some systems, but quite hard for other systems. The velocities, usually we don't care much, we'll talk about later. And a warning here is, when you build the system, you have to start with a good initial condition for atomic positions. Because for many reasons, you want to make sure that you are simulating the correct system with the correct structure. And many times, if you start with a bad initial condition, your simulation won't start. In 1 or 2 time steps, it breaks. And sometimes it's hard for the user to figure out what's going on. So usually the students say, oh, maybe my potential, maybe I have a problem with my file. At the end, it may be just a bad initial condition, have overlapped atoms that sometimes you can't see on a visualizer. And remembering, when forces depend on the interatomic distance. If they are too close, if your initial condition is not adequate, you can have almost infinite forces in your system, either increase very much the temperature or even break it, explodes. We're gonna talk a little bit more about that later. So the next step, okay, I have these positions. Now I have to compute the potential energy of the system, depending on the interatomic distance, and compute the force. So we have to use interatomic potentials, and maybe it's the most important warning of all of them. We have to use a suitable interatomic potential for both the system, the species, the molecules, the solids that you are simulating, and for the properties you want to compute. There are many potentials for carbon. For example, I can take only, for example, reacts. There are over 10 dozens of parameterizations with carbon. You have to choose one that's suitable for the type of molecule or solid you are simulating and for a given property. So one potential or parameterization that's good for example, combustion is not good for example, mechanical properties involving carbon systems. So it's very important to check, we're gonna talk more about that later, the suitability of the potential. To get new configurations over time, you have to use an efficient ODE solver. Usually we use explicit ODE solvers. This is the one that Kalina showed yesterday, the most used, the velocity verlet. At the end, we don't have to implement anything, just choose the integration time step. And that's another point that people sometimes overlook. You have to use a suitable time step. What I mean with that? For example, if you have to run your simulation for a given time to observe your phenomena, for example, 1 picosecond. If you use a time step of 1 femtosecond, you need 1,000 steps. If you reduce your time step to 0.1, you will need 10 times more steps. So your simulation will take 10 times longer. So you have to find an equilibrium between efficiency, run simulations in a reasonable time, but keeping the precision. We're going to discuss a little bit on that later. How to compute properties. Usually we have traditional equations from statistical mechanics that connecting macro properties with microscopic information. And my warning here is be sure that you want to compute average when you're analyzing a system equilibrium after proper equilibration. So you need to give some time for the simulation to really reach the equilibrium. Then you start taking samples to compute average. Sometimes just people get the whole atomic trajectory to compute an average property. That's not correct. The standard method, as discussed yesterday, this is a conservative system, so we have configurations in the NV ensemble, but we can simulate systems at temperature and pressure and constant temperature pressure using algorithms called as thermostats and barostats that Kalina showed yesterday. And we also want to impose some external driving forces. Mechanical strain, artificial heat fluxes or mass fluxes, gradients, and all of these methods usually has parameters that are intrinsic to them. And you cannot use like random values for these parameters. So you have to choose I'll show later some examples. The most adequate parameters to conduct the simulation, and sometimes you have to carry out convergence tests. You need to get results that does not depend on these parameters. This is a numerical parameter, so your solution shouldn't depend on these parameters. So we're gonna see some simple examples later on my talk. So this tool allows us to simulate equilibrium and non-equilibrium processes. It's important to mention that in molecular dynamics, we try to simulate real experiments, but on a shorter time scale than typically used in a lab. So in a lab, your analysis can take seconds, minutes, hours, days. You are trying to observe the most important, the most relevant phenomena happening on this scale. It can be an apparent limitation, but we can capture the most important phenomena, and a wide spectrum of relevant phenomena can be observed in MD. On the other hand, due to small time scales, some phenomena may not observe in the simulation. So some examples were discussed yesterday by Kalini. You can have simulations where you can't sample relevant microstates because of the time scale that you are using. So you need maybe probably to find another methodology such as Monte Carlo. But it's good to keep in mind this time scale that we are interested here. So there's a lot of books that I suggest for MD. I think that an easy one that is pretty good is LAMP's manual. I'm gonna talk a little bit more on that later. And nowadays there are many softwares and packages available to carry out MD. So yesterday, Julian showed LAMPs, Eudes showed GROMACS, and you have the tutorials, the hands-on experience, and there are many more. I started in my PhD with molecular dynamics, and my advisor just told me, okay, you have this problem to solve, go there, build your own MD code, and figure out this problem. Wow. I loved programming at the time. I had previous experience with numerical methods, computational fluid dynamics, and so on. And I liked the idea, so I implemented my first code. It was very nice. I could combine with the Aribo code from the original authors. It took me some time. I learned a lot. But every time that I needed to do something new, it was very hard because I had to first learn the method in details, implement, test, validate. And after 2 years, 3 years, a student in the lab said, oh, have you seen this LAMPS package? Well, let me see. Wow, it's much better. So when I looked back at my code, I felt like I built a car like that. I had a lot of fun. This is Marcos Tacalepau, you guys might remember. I had a lot of fun. The car could move around. But you see, I couldn't go much further with that. So when I saw the other codes, I comparing them to different cars. So, of course, I started learning LAMPs, and now from that on, I just use LAMPs. And I brought these images to bring some ideas on some discussions that we had in the previous days. Now, first of all, of course, there are years of many engineers working on these cars. Of course, they are going to be better than one guy in your backyard building a car. Of course, it's going to be likely much better. But the other thing is the following. Which one is the best among these three? What would you say? Depends on the situation. Some people say, the Ferrari, the Formula One, of course, is the best option if you are in a circuit that you have very smooth, so you can drive fast. But it's useless if you're gonna to a rally when you have mud and dirt and sand and deserts and jungle. So it's useless. And both of them are useless if you are in Porto Alegre or São Paulo in heavy traffic and you have to move very slowly and you have small parking stops. So the Uno would be a best option. So, okay, what has to do with this? It's the same. There's no better option among these ones. Each one was developed toward a given object and they do pretty good some things, but they're complementary. In some situations, I would like to have a Ferrari. In other situations, I would like to have a Jeep. It's the same with these tools. So like you said yesterday, probably if you are going with organic molecules, biomolecules, go with GROMACS, GROMAS. But if you are, for example, trying some things with Reacts, with Comb, Aribo, maybe go to LAMPs. So that's my message I wanted to bring with these images. Another message is the following. For example, it's good to know how a car works, how a combustion engine works, a transmission system. but it doesn't necessarily, those are all the ingredients to make a good driver. So it's possible to drive this car, to be a good driver, even though if you don't know what's going on in the engine. So that's what I mean by when you start using these tools. You don't have to know all the details. For example, Paul Pitts showed those potentials. It's impossible to know all the details of reacts or comp. But if you know how to drive safely on this car and safely and in an efficient manner, it's enough. So with these modern tools, maybe you don't have to go deep in the details of the methodology, but you have to be aware of what you are doing. You want to make sure that you are driving in an efficient manner, in a safe manner. So it's the same message that I can give about starting using these tools. But I personally use lamps. So why lamps? Why I would, for example, suggest someone to use lamps? So as Julian said yesterday, it's an open source. It's free, a lot of contributions from groups. Usually with, nowadays when new methods are developed, people are going to lamps and they make it available for the community. This is very good. It's quite efficient for parallel computation. It has an excellent manual. I've worked with many open source softwares. I would say that this manual for lamps is maybe one of the best, if not the best. It has examples for applications, details of the implementation, and more details it gives. Oh, you can find more details in this paper. It's pretty good. It's quite versatile. Why versatile? You have many options for state-of-art force fields and interatomic potentials, and you have a lot of already implemented tools for both equilibrium MD at varied ensembles and non-equilibrium MD. So usually you don't need to implement nothing new. You just can learn how to use. And it's the same thing that Julian showed yesterday. And if you have experience in any other MD code or MD method, it's quite easy to learn lamps. So don't get scared with it, because if you know all those steps that I showed you in the beginning of my talk, you can find directly the codes, the commands that are used for each one of the steps. So this is a typical lamps code similar to what Julian showed yesterday. So the manual, as I said, you can find it online. You have details of all the commands. For each command, you have a thorough description, examples, limitations. It's wonderful. So I always suggest you want to do something new, go to the manual. Probably you'll find what you need. It has a wide library of interatomic potentials. So most of the potentials that Paul Pitts mentioned this morning, EAN for metals, EDIP, Steiner-Weber terms of Rieber, blah, blah, blah. Everything's implemented. You can find the pieces to compose those traditional force fields like CHARM, OPLS. You have models for water. So it's quite comprehensive, the collection of interatomic potentials. And in terms of tools, we have tools to do a lot of things, different things that you can use in equilibrium, non-equilibrium. We have different ensembles. You can apply different kinds of deformation in your simulation box. You can use those methods for constraining bonding angles discussed yesterday. Now we have some tools with Monte Carlo already implemented, and some specific tools for non-equilibrium molecular dynamics to compute thermoconductivity, viscosity, for example, and a variety of boundary conditions and constraints that can be applied. So before starting any analysis, check the manual. You are very likely to find existing tools that will do what you want, like the fixes over 250 possibilities, computes over 100 possibilities, and you have the option of create your own variables in computation of properties. So when you see lamps, you say, okay, everything's all set, let's just use it. But what should we do to ensure the success of the simulation and obtain reliable results? Because it's quite easy to run lamps and use sophisticated potentials and sophisticated methods, but it doesn't mean that you will not get a reliable result. Okay, it's very easy to get results that are beautiful. You can see those movies similar to Paul Pitts. In the case of Paul Pitts, those are accurate results, but sometimes you go to conferences or journals, you see those wonderful movies, but you see the settings of the simulation are not consistent. So what we can do to guarantee that we can have good results? So Paul Pitts made my job easier talking about the interatomic potential, so just focus more on the selection, more the practical point of view. Validation tests, why they are important? In the sense of people are asking, every time I have to simulate a new system, I have to reparameterize Reacts, or can I use those parameters that these guys develop? So the best way, okay, go do your homework, check, do some validation tests and see if it works for the system that you want. Some problems that we usually have with initial conditions, and in terms of simulation parameters, some convergence tests. These comments are kind of general for any kind of computation. I'm gonna give some examples specific for material science, but of course you can use in any other kind of system. And it's nothing complicated. I want to make things easy because they are relatively easy to carry out. They are of fundamental importance, but I see that sometimes overlooked. People don't care. People get the tool, starting getting results, write a paper, get your thesis, and that's it. But I can say that many papers I've read and reviewed as a reviewer with Reacts and Aribo, it's a bunch of crap, sorry. But people just get something that's already implemented, use, get some results, non-physical results, and try to explain it.
That's what I commented in my talk. I just want to say it again. I was not saying not to use LUMs or any package. I just want to say that it's, you have to know statistical mechanics, you have to know these kinds of things to make sure that you are, for example, in equilibrium and things like that. And for example, if you want to simulate some liquid and you know this equilibrium, you want the properties that depends on equilibrium, you have to run many
replicas many times, yes, yeah.
To see if they all converge to the same properties, etc., etc. So my message maybe was misunderstood.
No, I saw your point. Actually, there are people that do exactly what you said. You just use the tool, they don't know anything about the method.
And I think that your example made me change my mind, because yeah, I did my car probably worse than yours, and I just find cars to use that I try to learn how to drive them.
Yeah, we also have some love for our baby, our code. My code, for example, I wrote like for my early papers. Some of my best papers were obtained with that code, but it was limited in some sense. So that's the idea, yeah. All right. So just go very quickly over interatomic potentials. Pitts gave a very nice talk on the subject. Kalini Esser also showed some force fields. You have to model different types of interactions involving chemical bonds, involving intermolecular interactions, using analytical functions. So these functions usually has to reproduce curves qualitatively looking like that. So remember, the force is minus the gradient of the potential energy. So in case of intermolecular interactions, for example, van der Waals, it has to be able to predict the repulsion and the attraction properly. The same for covalent bonds. You have to provide like equilibrium bond length and frequencies of vibration consistent with reality. And for reactive potentials, I have to consider the possible dissociation. So these interatomic potentials or force fields are analytical functions, from very simple ones like Lennard-Jones to very complex ones like Reacts and Comb, like showed by Paul Pitts. All of them contain empirical parameters that have to be estimated, and usually we do that by fitting into quantum calculations for these energies and other properties, as well as to experimental data. Some potentials for metals and ceramics, sometimes you can fit to elastic constants that you can get from experiments, data from crystallography, and so on. So I would say that selecting appropriate interrelated atomic is crucial for accurate, reliable results. That's the first step. You will have to make sure that the physics at atomic level is correctly, accurately predicted. You have to make a sensible choice based on experience with the potential, success in previous applications, validation tests, verification of the data set used in parameterization. Most of the people don't do that. They just use like blind faith. I'll say, okay, someone told me that this potential is good, this set of parameters is good, I'm gonna use it. But it doesn't cost you anything to download the paper and see if the paper give you predictions of systems that are close to the one that you are simulating. There are several classical potentials, as showed in the previous talk, each one with a specific field applications, both in terms of species that you can involve in properties that can be predicted. And as Palpit said, the same potential can be used in different systems by reparameterizing them. We can use different set of data to get new set of parameters. And I say that the set of parameters is as important as the choice of the potential itself. You can say, I will use React. Okay, React is a good tool, but which parameter are you using in your calculations? This is as important as choosing. I'll talk more about that later. You have different force field, the pair potentials, the simple ones like Lennard-Jones, Coulombic, Morse. Some of them are used to compose those traditional force fields that were presented yesterday for biomolecules and soft matter, Charmoplas, Gromos, Amber, and so on. We have these many body potentials. Some of them are reactive, some or not, with different fields of application. We have some that are specific, for example, BAM for metals and alloys, Ribble for hydrocarbons and carbon allotropes, carbon nanostructures. And these ones are quite generic that can offer like many different parameterization. Palpit's already discussed that the parameters are estimated using experimental data and ab initio calculations, or just one of them. Usually, to parameterize a structure, we use a potential, we use molecular structure or crystalline structure, relative stability of different structures or conformations. In the case of adsorption or formation or breaking of reactions, binding energies, formation energies, adsorption energies, some physical properties like elastic constants, elastic modulus, compressibility modulus, vibrational frequencies from first principles, potential energy curves, curves in surface, in order to get accurate activation barriers between states, either for reactional processes or diffusional processes on surface. And it's always desirable to find, what Palpit said, a transferable parameter set. He explained usually you use a given data set to parameterize your potential. And if it's transferable, it means that you can use in a similar system and it's going to predict accurately the same phenomena. But you have to take a lot of care. We don't have to trust blindly on this. Usually we need to do some validation tests to check, to ensure that it's indeed reproducing the important phenomena. We're going to talk a little bit more on that later. And of course, I like mentioned yesterday, there's another option that's conducting ab initio MD, that you use ab initio methods, for example, the FT leading to the CPMD and BOMD, that I guess it's going to, we have 2 talks tomorrow discussing about this methodology. The advantage is that you can get electronic information along the way. That's it's very nice. And there are no empirical parameters. However, the cost is quite high, and we limit to system with like few 200 atoms up to picoseconds. While in classical MD, we can reach millions of atoms and nowadays up to microseconds. So we can study larger systems at longer time scales. And some people say, just matter of time. When you have better computers, maybe you're going to do everything ab initio. I disagree with that. I think that classical will always be very important, because if you can do that faster, you can do that even faster. So you can simulate maybe a system, the micrometer and the centimeter length scale up to seconds, so we can get more realistic information. So I think that's going to stay around forever. And it's important to mention that if you have a potential that's correctly parameterized, accurate parameterized, like some of the cases that Palpit showed, that can allow a proper description of the phenomena you are interested in, you can have the same accuracy as these quantum mechanics calculations, but with a much lower computational cost, provided that these requirements are fulfilled. Other aspect that's important when it comes to choose of the potential, I think nobody said in the previous talks, that's the computation of these forces that are the most time-consuming task of the simulation. So it always needs to be taken into account. So here are some statistics. I just got 3 random output files from previous simulations. And LAMP's print at the end of the simulation, the percentage of time that it spent doing certain tasks. And you can see that for all cases, different potentials, different tests, most of the time is spent computing, because the pair time is computing these forces. Why is that? Because these potentials, the functional formulas, this U is quite complex, as showed by Paul Pitts in the previous talk. And the other points that you need to compute derivatives. So for some force fields, it's easy to derive analytical expressions for these derivatives, like yesterday Kalina showed for the case of Charm, where you have the contribution of bonds, angles, it's easy to obtain the derivative. But imagine those functions that Paul Pitts showed for react, it's impossible to have an analytical derivative for that potential. So you have to do numerically, you have to disturb every atom on the system and compute these derivatives. In the end, you have to pay a lot on that. So it's other thing that you have to take into account. If you have an expensive potential, your simulation will cost a lot. So this is a plot similar to what Julian showed yesterday, some benchmarks made with lamps for different potentials. And the metric is a ratio to a similar simulation, similar number of atoms, similar time step and everything else, proportional. And you see that depending on the potential, you can have, for example, a variable 54 times lower reacts to 56 in comb 585. So it means a simulation that can take, for example, 1 day using a variable will take 10 days using comb, for example, using the same number of processors and the same machine. So it's always important to take also into account the cost, the computational cost, because as I showed in the previous slide, the most expensive computationally speaking part of the method is computing those forces. And of course, even though React is more costly than the other methods, it can compare with like semi-empirical and ab initio DFT. They are orders of magnitude different from each other. This is from the classic paper of Van Duyn when he introduced React. He wanted to show that you can get similar results, accurate results, but 1 million times faster. That's the point of this graph, this plot. So again, you have everything already implemented in lamps. You have some specifics for the systems, for these ones, for example, for metals, called solids, some reactive. Even can do some coarse-grained MD simulation, as explained yesterday. It can be done in lamps. And you have like some flexibility, always to, of course, to implement new potentials and to use these hybrid styles. I say you have to take a very good care of that. What is hybrid? You can combine these potentials. This can be disastrous most of the time, but it can be very, very useful in some situations, like these ones. You can model polymers with charm and metal with EAM and somehow make them talk to each other. And here is what I said before, because it's easy, people using React or Aribo on lamps. It's quite easy. You build your system. You just need your coordinates, X, Y, Z. You don't need topology information because, as Paul Pitts said, based on the chemical environment, the potentials are able to define the bond order, if it's a single bond, a double bond, a triple bond, if it's a radical, or if you have a conjugate system. So you just need to provide X, Y, Z coordinates that are the easiest one to get. And you just have to set up what's the style, you say, Aribo or Reacts, and set the coefficients. So you have file containing parameters like the ones that Paul Pitts showed. That's the case, for example, for one of the parameterization of Reacts, 124 lines, Aribo 37,595 lines, is a huge file because of those spline functions that he mentioned before. But you don't have to worry, you just have to get these files and your simulation is all set up. So it's easy to do, but again, you need to be careful which potential you're gonna use and which parameterization you're gonna use here. So these parameters in lamps are available in the installation folder potentials. So if you install lamps, there will be a folder called potentials, and you have dozens of interatomic parameterization for several potentials, 2, 3 for Aribo, many for EAM, some for ReactFF. And these are well defined. Is something that I tell my students, of course, if you get this file, don't do anything to it. Don't put a 0 here, don't delete any line because the result can be disaster. So get this file, put in your directory, don't touch it. We have also some good repositories on the web, so you can check this website. They are doing a great job at collecting files suitable for lamps and other softwares as well. for different potentials and different materials. It's a very comprehensive. So you go, for example, carbon. It's going to show hundreds of files with different potentials. Reacts you can get as a supplementary material of papers. So every time Van Duyn and some collaborators develop a new parameterization, usually they give as a supplementary material, just a matter of putting on a TXT file and using lamps. And for this potential, it's quite easy to set calculations up. For these first fields, lamps does not, it can do, but it's very hard to make it work. The parameters must be defined case by case, I'll show, and lamps don't do topology analysis automatically, assignment of parameters. There's something funny on their website that they show lamps features, what lamps can do. And because they have so many questions, can lamps do this, can lamps do that, they had these lamps non-features. So I said, okay, it has these features, it has non-features. Okay, lamps doesn't do that, you can ask me 100 times. My answer is always no, it's like the guys in the forum said. And some of the things are these. It can be used to building molecular systems or building molecular topologies that are needed for CHARM or PLS, and assign first field coefficients automatically. Magically, like something that just put in. There are a lot of questions on the forum. Can I use CHARM? Can you give me an example? Can you build this file for me? And the guys in the forum, come on. It's your work. You are the student. You are the PhD student. Go find a way of doing it. So we got started a while ago in trying to do some calculations, for example, with polymers. And of course, a lazy way would be, let's get a Ariba, predict wells, hydrocarbons. Let's just use it. But a Ariba is very computation demanding. And there is always the case of transferability. So we decided, let's implement CHARM, and we have to figure out a way of doing it. So just one example, advertise a tool that we developed at the lab. For example, this is a ethane molecule, quite simple. You have the XYZ coordinates that usually is enough for lamps. But if you want to use one of these potentials, you have to provide all the topology of the molecule. For example, atoms, where are the bonds? So you have, for example, 7 bonds, a bond of type 1 connecting atom 1 and 2. So it's a carbon-carbon bond. And we have to provide all the possible angles and dihedrals and provide all the parameters of the pair contribution, the bonded contribution, the angle, and the dihedral. You have to do by hand or use a different tool to generate the topology, copy, paste, and go to the file of CHARM, look for these parameters. It takes a lot of time to do something as simple as that. So what we did, we tried to develop a tool, a Python, a collection of Python scripts that does all the jobs. So we can get the same XYZ files that we usually have for our simulations in lamps. And this code is able to do all the topology analysis and assign properly the parameters and creating these files as lamps requires. So I'll show the slide later again. The name is ChemStruct. If you Google ChemStruct, you're going to find other tools, softwares that there's nothing to do with us. So here's some example. Pedro Domingos is an undergrad. He just graduated and started his master's. He did a really great job creating this tool. Basically, what it does is, given the interatomic distance from the XYZ file, we can identify what are the bonds, the dihedrals, the possible hybridization depending on the neighborhood, how many atoms are bonded to each one, and classify according to a specific force field. In this case, this is a carbon from a methyl group, sp3 with other carbon. These are hydrogen atoms in a CH3 group, and we can connect it with the description given by a potential, for example, CHARM. CHARM recognizes the sites by these tags. So we can go over the parameter file of CHARM that has thousands of lines, look up on this table where are the parameters for this given species, and do all the job for us. It's very nice. It works well for the systems we use up to now, but it's very important that more people use it. So if someone is doing a similar kind of research, please use it. Tell us the bugs, the problems. It's always good to have this feedback. So you can imagine if this file is quite long for a single ethane molecule, imagine for a polymer like you want to study. The file has thousands of lines, impossible to do by hand. So this is the name scheme structure. You can find on GitHub, you can install, you can use it, and you're gonna find there our emails. You can contact us if you have any problem using or find any bug. They are very welcome. So up to now, just a summary what we discussed on interatomic potentials. There are several potentials, as Popitz had shown before also, for variety elements and various purposes. LAMPs offers several state-of-art potentials. Adding parameters is simple in some cases, just use those files that are already done, but not always. Sometimes you have to do some coding to tell LAMPs how the interaction should be computed. LAMPs allows for easy inclusion of new potentials and variation of the existing ones. So it's very nice to have the opportunity of implementing new potentials. People are doing that all the time. So usually you find a paper, this guy did an improvement on IRIBO. And at the end, said, okay, I implemented in LAMPs. You can go there and check and test yourself. That's very nice. And LAMPs make things very practical and efficient. So it's easy to set up calculation, but you must be very careful. Because again, selecting interatomic potential is the most important part of the simulation. You have to take into account the phenomenon and the property that you are interested in, the accuracy, the limits, the computational cost. These interatomic potentials are usually already implemented in these packages, so you have many options for the same system. And of course, they can be offered in different flavors, different parameterizations, and choose a suitable parameterization is as important as the potential select. If I had to summarize everything that I said, and I'm going to say in the next slides, is this sentence. Use a potential with parameterization where it can be used, or it must be used. There are some parameters that has to be used specifically for that system, otherwise you're gonna get wrong results. And how to do it? It seems, okay, you are telling me I have to check. Okay, but can you give me some hints on what to do it? Personally, we follow this, not all of them now the case, but most of them. First, we search the literature for previous works employing the potential and parameterization in order to evaluate the success in similar applications, what people could do if they had some testing, some validation with the FT, if they could corroborate results from experiments. So it's good to check. It's always good to check the data set using the parameterization. You can get the paper. I'll show some examples in the next slides. You can see what are the species involved, what are the properties that are measured, and check what's the accuracy of the potential to predicting these properties and what are the limitations. And it's not enough. Sometimes you need to carry out validation tests. You can conduct initial tests using molecular structures, sometimes simpler than the one that you want to study. So you can do also some DFT to compare. You can also compute some properties related to desired application before going to the full problem. There are small tests or even large tests that you can do just to make sure that the potential is predicting what you wanted. And this validation can be done using either experimental data, observation, or other type of calculations, either using other potentials already validated or ab initio. So for example, if you want to work with carbon, RIBO and IRIBO, it's an excellent choice. And you can go there and see, they fit the data with quantum mechanic curves, potential energy curves, and some relative energies. And you can see, for example, how good it can predict, for example, properties of diamond here, some elastic constants, the interatomic distance, bonding energy, vacancy formation, and you can compare experiments, and you can see that the agreement is very good. So if you want to work with diamond, it's a good choice, for example, or something similar to diamond, as I'm going to show in an application later. Same for graphite. You want to study graphene or nanotubes or something similar, you can see that it does a good job predicting some properties of graphitic structures. We can check also entropies of vaporization, conformational energy, differences between conformers. Sometimes you can get the barriers for the torsions, bond enthalpies, and always compared with experiments. So you can make sure if I'm studying a system similar to that, it's guaranteed that you're going to get decent results. So it's always good to go back. This is the original paper of IRIBO. It's good to go back to the original paper and see what was done there. So you can have, you can be more safe in your choices when you are applying this. So this is one example of Reacts FF that show, for example, you can see your compounds and see if where they are on these curves in terms of heat of formation, comparing the experimental and the calculated. You can see that the agreement is quite good. Probably some of them were used on the parameterization, others were used for validation purposes. You can get geometries and compared with experiments for some bond angles. You can get, as I said, bond dissociation. So if you are interested in studying, for example, ethane dissociation, combustion, so on, you can see that it predicts relatively well the dissociation of this molecule. You can compare directly the curves for different systems. Here is, for example, a reaction between hydrogen and CO that is important in many oxidation processes and other reactions. We can compare, for example, angle distortions, dihedral distortions, and compare with the quantum mechanics and see how good. So these are different papers with different parameterizations, usually with, for example, in the case of Reacts, when Van Duyn is a co-author, he makes sure that these results are presented so the user can read the paper and say, okay, I can use this potential for this specific application because it works well. Even some more complex pathways, so he's an oxidative dihydrogenation of propane on a vanadium oxide that you have many steps. So you have here the curve obtained by quantum mechanical calculation, the curves by DFT, and you can see an excellent agreement. It can predict all the intermediates, can predict accurately the barriers. So if you're going to study one process related to that, you are very confident to get good results. So it's always good to go and check these papers. And of course, sometimes it's not enough. You have to do some validation. So here are some examples. My student, I just asked her to run some calculations to see in terms of structures and energetics of different carbon allotropes and nanostructures with different potentials. They don't agree with each other. Some of them are closer to the experimental than others. In some cases, you can't get the result. For example, there are some Reacts parameterizations that they can't predict something as simple as graphite, for example, graphene. It predicts a distorted structure. The bonds are not equivalent. And of course, very far from the experiments. And same thing here for example, energetics or energy of adhesion between layers on graphite. So this is the experimental value. IRIBO does a good job, but Reacts always overpredict. It's not a bad thing. It doesn't mean that we can't use these parameterizations, but at least you know that I'm overpredicting the result. That's another point. It's difficult to find a potential that will match exactly your results. But most of the time, it can provide you a good qualitative picture, and you will know at the end if that property that you are calculating, you are over-predicting or under-predicting. It can allow you, for example, some studies to set, this is the maximum value I can get for these properties, or is the minimum that I can get. So in that sense, we have to use our critical thought. So here was one example, more details of, for example, mechanical properties that we do a lot in our lab. So this carbon nanothreads is a new class of materials that was synthesized in 2014, 2015. Julian showed something on Tuesday. It's basically benzene rings that are fused to each other in a one-dimensional chain, and it can be arranged in many forms. So after the experimental study, 1 year later, a group said, okay, we computed the mechanical properties of these carbon nanothreads. They are stronger than graphene and stronger than everything else. Now, come on, that not can be true. Because nanotubes have sp2 carbon, here you have sp3 carbon, you have different possible configurations. So we wanted to check. So we just compared, for example, they used this potential with the CIAN curves. Of course, they got a very high value for the properties. This one is quite used for nanomechanics of carbon. A lot of people have used this potential. It's the one by Miller. I forgot to put the reference here. IRIBO, that's also widely used, and we run some, for example, some DFT calculations. And we can see that, for example, for this structure, IRIBO does a great job at getting the linear region and the region where we have fracture. And these potentials kind of overpredict both the fracture strain. In other words, they strained more than they should before breaking. And of course, they're going to provide higher stresses. And even some weird behavior appeared in some of the curves. We can see some plateaus, some changes of inflation. So we first saw that depending on the system, some properties can be better predicted than others. So we figured out what's going on. Then we can see that there were several problems. One of them, like for example, for more exotic structures, here you can see that IRIBO does a good job, but it doesn't happen for the others. Why is that? Actually, because this structure resembles diamond a lot. And I showed in that slide before that IRIBO does a good job with diamond, so I expect that it's going to work in something similar to diamond. But these structures, they are all sp3, but not the same sp3 as in diamond. So we have this difference. And we can see that IRIBO couldn't predict consistently the structures. So we compared with the FT, at least reacts, even though the quantitative results were not good, the qualitative were, in terms of which bonds are most strained, where the stress is concentrated. And IRIBO predicts some very unusual structures, not symmetric, with some residual stress that didn't exist in the other methods. So we could see the situations where IRIBO works and where it doesn't work. The same for reacts. And here's some example. If we follow some of the bonds, the dependence of the characteristic bond lengths with strain, you see, it seems a fitting, but it's not a fitting. This is just a validation. We can see that IRIBO gets excellent results. This is a structure that's closest to diamond. Again, if you parameterize something with diamond, it's expected it's going to work with everything that's similar to diamond. But it doesn't happen for this. You have here, let's say, softer bonds, or some unusual trends, like you are straining, suddenly it jumps by 0.1, 0.2 angstrom. That's unrealistic. It doesn't exist. But the guys published a paper with the results without showing this kind of data. They just showed, oh, this is strong. See how beautiful these curves are. But they are wrong. So the purpose of this paper it was the first work to do an accurate analysis of the mechanical behavior and show that you need to be very careful when you use these potentials in materials that you haven't studied before. So nobody had studied nanothreads before. Nobody know about the existence of nanothreads. So it was a new material. So I have to be very careful in using these existing tools to new materials. I have to make sure that this new material has some properties familiar to the previous ones that we know, and that will help us to choose better options. So this kind of mistake is very common. I've seen a lot of papers where people just blindly trust in reacts, and they get like, I was reviewing a paper a couple of weeks ago, I can stretch graphene by 50% without breaking. That's impossible, 50% of deformation. So they just use a parameterization that was defined for oxidation of hydrocarbons, for example. Of course, it won't work. But people go there and publish it, and some reviewers say, good, good. And you see a lot of people, a lot of works that are published, highly cited, but with completely wrong calculations. That's something that as a scientific community, should pay more attention. Here, one example, a guy that studied in this paper, he just compared, for example, here's some plots. He has a comprehensive study on mechanical properties as well, comparing, for example, in this case, elastic properties of graphene, that was a hot topic and still is, compared elastic constants, elastic modulus, Poisson ratio. You compare with PBED2 with reacts. And you can see, for example, elastic constant of 170, PB gets 150, reacts 4,000. Completely wrong. But people publish results with these data sets. It's unbelievable. Here's some examples of curves. They disagree with each other, the FT and other different carbon parameterization. So just show that you need to pay attention to this parameterizations. Here's the other example, EAM, that Popitz showed. It's an excellent potential for metals. It can describe well dislocations and dynamics of dislocations and ductility, brittle behavior. It's quite nice. But if you go, for example, I want to study gold. So you go on the repositories, we'll find 10, 20 different parameterizations for gold. But someone told him, no, go with AM, that's good. You won't regret. It's pretty good for metals. Then you randomly pick up one of them, start using, get your results, and write your paper. In the end, maybe if you're lucky, you can get good results, but it's a matter of luck if you pick up the correct selection. So that's a recent paper or scientific reports. They do a comprehensive test for many of the most used parameterizations for EAM on the literature. So they got, I don't know, 8, 9 for each element. So they did for gold, platinum, and iron, and so on. And they compared, for example, people use a lot for mechanical properties. They just compared, for example, the elastic constants, 1, 1, 1, 2, or 4. And we can see that depending on the parameterization, you get good results. Like this yellow one, you can get here, not so good here, good here. But for some of them, you get results completely wrong. So it's always important, again, to show what's the purpose of showing these slides. The same thing, you can just get among these many options that are available, just use it and don't worry about it. Check the literature. It's very likely that someone had done that for you before. It's always good to start checking the literature. If you don't find anything in the literature, please do yourself. That's the best way to assure that you are getting good results. So some very unusual behavior to show here, just a case that happened a few years ago in my group. We are collaborating with a professor on degradation of organic molecules by free radicals. This towards treatment of residuals. So you have some dyes from the industry that they don't degrade on the environment. So you have to use a specific process for that. One of them is using oxidation. So you can use permanganate or something that generate free radicals, and these free radicals are going to attack the molecule and break in smaller ones. And ideally, it's going to bring just to CO2, water, some nitrates, and so on. But the problem is that these processes in the practice can generate species that are even more toxic than the original one. So they have a lot of studies to see, okay, if I apply this process on this molecule, what are the different species that I'm able to get? And at the time, I just got my position as a professor at UFRGS, and let's give a try and see what we can do. Then I put a student to work, and she was a pretty good student. We published 2 other papers in other fields, in carbon mechanics, but in the beginning she was doing some calculations, and she could start to find some very unusual stuff using reacts. So for example, she said, "Professor, I found something very cool. The OH radicals start bonded to other forms like polymers attached to the molecules." It doesn't make any sense. But the potential predicted, it gives a stable structure. It was stable and it lasted for many seconds. So it's another way, you can't just use a potential and expect that things work. So we had to do a test with different potentials, and we could find one of them that could do at least part of the things that we were interested in. But just to show that you can get wrong results, but they don't seem wrong, like those curves. If you see those curves, if you don't see the other two, you can say, they make sense. It increases, it breaks, fine. Sometimes it's hard to see that's wrong, but in this case, it's explicitly, you can say, no, it doesn't make it. This is oxygen. It's a ring of 6 oxygen atoms. It doesn't make any sense. But reacts predict, some of parameters predict this is a stable structure. So the summary of this part of the talk, you use a potential when it can or must be used. The success of our simulation depends strongly on the potential that you are using. There is a good chance of obtaining artificial, unrealistic results. Sometimes it's explicit, sometimes not. You have also to accept that sometimes you won't be able to get precise quantitative results, but you can use these potentials to obtain qualitative results, a better understanding of the phenomena, even though if you can get precisely some properties from a quantitative point of view. And always in that sense, no limitations. So if you do these validation tests, you know what can be done. If the results are over-predicted or under-predicted, you have everything under control. It's okay to publish a paper and say, I tested the potential. It could get me this, it couldn't get that. I'm aware of that. I'm not making any claim about these findings. Okay, it's okay. All right, so we have a suitable interatomic potential, but it's not only that's not the only part that I should care about. There are other things like providing a good initial condition, ensure a proper equilibration of the system before taking averages and maybe run several replicas to get statistical meaningful results. Ensure the results does not depend on simulation parameters. I'll show you some simple examples. So for example, in terms of initial conditions, you have like ethanol, it's easily to describe. You just need the XYZ coordinates. You have a lot of packages to do it, like Avogadro, JMOL, PECMOL to create condensate phases. But you have to create customized tools in some cases. Here are some examples. This is a porous carbon nanostructure. There's no software that can do that. Julian did a great job developing his codes and using Efficient, Ovito, and other tools to create these complex tools. Like amorphous structures like polymers, or functionalized surface like in graphite oxide, where you have to insert randomly or according to expected trend the different functional groups. So it's a kind of art. I can give some hints on how to avoid problems like with that. Like for molecules, it's good to use a software to generate, or you can get from databases. We can use tools from the Avogadro itself to run some previous relaxation before going to serious calculations. To create a solid and fluid phase, you can start from crystalline or disordered structures. It doesn't matter for fluid phase, the dynamics will induce the systems to disorder. But if it's solid, you have to use lattice parameters and internal coordinates as close as possible. And it's always necessary to carry out a preliminary structure optimization relaxation with the potential to be employed, because not always the bond lengths, the coordination, the angles will be the same. In a poor initial condition, besides, it can lead to different results. You can start with a structure, something happened in the beginning, it transforms in another material, and you're going to study something different that you wanted from the start. And also, a poor initial condition can make calculations unfeasible. So you can have problems of convergence. It's quite common. You create a system on Avogadro and other tools, and you start running a calculation, and it won't start. In the first step, it gives an error. This error, the message is not always the structure. Say, this part of the code didn't converge. The PPPM for calculating charges didn't converge, or not a number in some properties. It's basically because the atoms are too close or superposed. And at the end, all those potentials depend on interatomic distance. If they are too small, the force will be too high. They're going to repel each other. That can lead to high increase of temperature. The temperature go over thousands of degrees, or the system can simply explode in this case of reactive systems. Paul Pitts can say how many times, Paul Pitts, you tried to create a system and it was very beautiful. In the first step, it explodes. It's very common if you work with complicated systems, especially solid crystalline systems. So some hints, always optimize with your interatomic potential of interest. When using a software, maybe just use a simpler force field that is already implemented in this package, like UFF, GAF, to do a pre-relaxation. Start your simulation slowly. If you have to run a simulation at 1000 K, don't start at 1000 K. Start with a low temperature. Wait for the molecules to equilibrate, the vibrations in a solid to spread. Then you increase the temperature. It's a simple hint, but it's very, very, very useful. You can also, in terms of disordered systems, it's hard to create, so you can create a structure, heat them up so the molecules can travel around, or the chains can relax, and then you cool it down again so you can avoid getting trapped in local minima. Other hint, if you're having trouble in the beginning of the simulation, reduce your time step, and of course, start from various initial conditions to avoid this local minimum. Just some hints that you get from experience. Some of them are simple to carry out, but using combinations of them, I can assure that you can get simulations to run from the simplest to the more complex. Other things that you have to care about, how many time I have? 20 minutes, okay. Is this the choose of integration time step? Some things that we have to care about when you use periodic boundary conditions, thermostat and barostat damping constants, and we are imposing external forces. The objective is always to keep a stable and efficient simulation that will generate results that are independent of the parameters used. And sometimes there are needs to carry out convergence tests. I apologize, some of the slides now will be in Portuguese because it was a copy-paste. I was finishing last night, I got some materials for my lectures, so I'll continue in English, but some slides are in Portuguese. When it comes to the numeric integration, you have to consider that the cost of the simulation must take into account the total time and the time step. The smaller the time step, the larger number of steps. And the cost of each step is related to the potential. And remember, this is the most demanding part. So part of the simulation. So we have different methods to do that. Usually they are explicit methods. And some people that like numerical methods sometimes ask, why don't you use Runge-Kutta, for example? It doesn't work because Runge-Kutta, for each time step, you have to evaluate 4 times the derivative. Consider that computed derivative is the most expensive. You don't want to compute many derivatives. So we prefer using methods that are explicit. You don't have to solve any algebraic method, and something that doesn't require many evaluations of the forces. And one that's pretty good, simple to implement, it works very well for molecular dynamics in that sense, is the velocity varlet. We just have to care about the time step. So we have like some traditional values that people use but don't know why, and here's a hint on how we can estimate. For example, when you have hydrogen, people use around 0.1, 0.22 femtoseconds, carbon around 1 femtoseconds, copper 4 femtoseconds, and so on. So how can you assure that these values are suitable? You can say, a lot of people use and they work. Okay, I can accept that. But you can check. So for example, we can do use an heuristics that each time step the atoms shouldn't move about 1/20th of the interatomic distance. Considering that velocity, the average velocity is related to temperature, we can check what would be the average velocity of, for example, a hydrogen atom at 100K, 300K, 700K, is a mass of 1 atomic unit. And we can get the average velocity, considering that you have a distribution of velocities following approximately the Maxwell-Boltzmann distribution. We can guess the fastest one. The fastest ones are around 5 times the average velocity. And if you get this velocity and we get an interatomic distance of 1 angstrom, these are the time stepped according to these heuristics. So we can get, of course, the higher the temperature, the smaller the time step that must be used. And of course, you are always conservative. That usually we take these values like 20% below. That's a good heuristics that if you want to figure out, I have to simulate gallium, I have to simulate iron, how can I find a suitable? You can use something as simple as that. So if I repeat this for heavier atoms, you see that for the same temperatures, I can use larger time steps, and these are some typical values used in the literature. Usually, when you have light atoms and or high temperatures, you are required to get smaller time steps. When you have heavier atoms, like for example, some metals in low temperatures, you can use larger time steps. Remember, the smaller the time step, the most costly the simulation. So it's good to try to use an optimal value. Of course, as showed yesterday in other talks, you can use some methods that can constrain, for example, carbon-hydrogen bonds, and you can save a lot of time doing that, about 10 times. You can use time steps 10 times higher to do the same kind of simulation. Other thing that you have to care about, Kalini showed briefly, I'll do the same here. When you control temperature and pressure, you have, independent of the method, you have a coupling constant that says if your response, for example, to a change of temperature is fast or slow, and also control the fluctuations. When you have different examples, you can have different types of responses. And it's all a matter of choosing a proper coupling constant. How do you do that? Best thing, run some tests and also check the original method. Usually the author says, you can use this constant around this time or proportional to your time step. The LAMMPS manual also gives some hints. It's always good to check this because it's going to affect when you compute average, or if you're just interested in equilibration, it can make all the difference. So it's something that you have to take care. I'm going to run a little bit to show some of examples. I have 10 minutes, I guess. When you use supercell, when you use periodic boundary conditions, it was explained yesterday. You have the simulation box, and you define your boundaries like if it's bonded to identical ones. So you can simulate an infinite system. So you can simulate bulk in 3 dimensions, or a 2D material like graphene, or even a 1D material like a nanotube, a nanowire, a nanothread. So of course, the larger the dimension of the system, the larger the computational cost, but it's a system more realistic. You have to find an equilibrium between cost and quality of the results. So something very simple. This is not exactly a toy problem, but it's simple to solve. We have a nanotube and we are deforming it and observing how much stress is required to break. And we can see that depending on the time, on the length of the nanotubes, we can get different results. So basically, we increase the size of the nanotube until a value where we don't observe further increase on the property. So I can afford a system with 12 instead of 20. It's cheaper. It gives basically the same result. This is what we call a convergence test. You get your parameter that you can control in your system, your methodology, and you changing it until you don't see any variations on the property. This is very important when you do a series of calculations. Other parameters are also intrinsic to the method, as I mentioned. So you have to pull the nanotube at a given strain rate. And these strain rates are quite higher compared to experiments due to the time scale used. And again, you have to find the lowest the strain rate, more time steps you need in the simulation to reach the same strain. So we wanted to use higher time strains. So of course you have to reduce the time strain, the strain rate until a value where we don't observe significantly changes on the property you are measuring. So this is important before doing any set of calculations for in a given project. It's important to check these parameters, always varying the parameter of the simulation and seeing that they don't affect the problem. It's the same thing as we do in DFT with the cutoff energy using plane waves and the K points, etc. So in summary, there are problems in conduct simulation from a bad initial condition and also using some parameters that are not suitable, and some of the times it's needed convergence test to guarantee results with quality. So that's what I wanted to talk, but I have how many? Because I wanted to show some examples, maybe 5 minutes more, 10 minutes more, okay. My idea is not to provide a comprehensive collection of works of our groups, just some works with MD that's related to some of these applications, some of these topics that I discussed. So we do a lot of mechanical behavior and mechanical properties for carbon-based materials, either existing materials, novel nanostructures. We understand how structural modification will affect the properties of existing materials. So what are the tests that we usually do? This is the classical one, uniaxial tensile strain. We just apply strain along one of the directions. If the material is anisotropic, we have to apply independently in different directions. Then we can compute the stresses along the trajectories and obtain these curves. So based on velocities, forces, and positions, we can compute the stress. And of course, from these curves, you might remember you can get the tensile strength, the ultimate strength, fracture strain, and the linear region, the Young modulus. We can also use different types of mechanical deformation like shear. So we can compute shear modulus by applying forces in opposite directions on surface. We can do some non-indentation tests. This is widely used in real experiments. It's easier to do than doing the conventional tensile strain tests. They have a substrate with holes on it, in this case silica. They deposit graphene and they put an AFM, atomic force microscopy, and basically what they measure is the indentation depth, how much it can go on the system or on the surface, and how much force is being applied on the tip. So using some models, they can fit this data to some curves and predict the elastic modulus and the maximum stress at rupture. I'll show a few examples of one of the cases. This one, a type of material that's a hybrid of diamond and graphene that we proposed in some previous studies with my former advisor. and we investigated electronic properties and structural properties, and then we went to compute mechanical properties. Some years after, we found this study, others that came after that, that showed experimental evidence of these materials. This graphene looks weird because they are rotated with respect to each other. When you have two lattices, if you rotate, it generates a Moiré pattern of the superposition of atoms and generates domains that are suitable for interlayer bonding to form diamond-like crystals. So we found that this material exhibited a very interesting mechanical behavior depending on the nature of these domains and the distribution. For example, some of them we just ran some calculations to see how strong they are compared to diamond and to graphene. So we can color the atoms according to the strain. We can identify what are the weakest point on the structure that we will see. It will be on the border of these nanocrystals. So from several tests, we observe the same trend. The fracture starts on this boundary, and this is boundaries, and it spreads, leading to a brittle behavior. So we can compute these properties as a function of the fraction of sp3 carbon. We could validate, of course, the values with graphene. It would be 0% of sp3. And we also compared with some results from the literature for randomly cross-linked graphene. They had the same chemical nature of our materials, but they are not as ordered as us. And we can see that the values predicted for the Young modulus are in this neighborhood, very close to our results. So always good to check our computation with experimental results, even if we cannot make a direct comparison. So this is one example what we can do in terms of tensile strain. We have many works. A continuation at some of the materials of this family exhibit a different mechanical behavior, a ductile behavior instead of a brittle one. So we investigated what in this paper we published last year, what's going on the systems. So we can find some metrics that detects for that class of structures what's the fraction of sp3 that can lead structures from a brittle behavior, as we observed in the first in the animation, to materials that suffer completely ductile. So we can compute properties and also observe different mechanical behaviors for the same material depending on the nature of the system. So we studied for a while also graphene nanomeshes is graphene with pores. They are having interest into fats and molecular sieves. And our objective was to see how strong graphene remains even though you have these holes. So we published some papers. Now we are revisiting some calculations with nano-indentation. They are close to the experimental one. So basically what we simulate is the contact of an AFM that's not showed in the movie. It allows to observe better the formation of the material. Then we can see how stress distributes along the material and compute this curve. Then we can fit that model and predict the elastic modulus and the fracture for different porosities and different distributions of pores. So we can get, these are experimental results for graphene, and these are our results with graphene. So you can see it's quite close. We expected that because, as I showed, the Aribo shows predicts quite well the elastic properties of graphene. We could also get a good result for the stress, and of course, we validated that we could extend and use to predict what happens when we increase the porosity. And now we are finishing a further analysis that we are investigating different patterns when you are applying nano-indentation on the fracture. Depending on the distribution, we can find some very interesting behavior, but it's not finished yet. This Julian showed during his talk. We also can not only predict mechanical properties, but understand what happened with the structure. We can see some interesting transformations that he used. I'll show later if I have time, to gas separation, for example. So we can see what happens to material when we impose different types of deformation. So this tool is quite good for this kind of calculation. We also do a lot of reactive simulations, a little bit different from pulpits. For one of the cases is to understand for example, it has an industrial application. People usually get polymeric membranes for gas separation, and they convert what they call carbon molecular sieve. What's the difference? You get a polymer, then you pyrolyze it, high temperature in an inert gas and form a more dense structure, porous. And usually in the experiments, they use microscopy, spectroscopy, and they see, you have a coexistence of amorphous carbon, graphitic carbon, several functional groups, but nobody knows what's going on microscopically. So we run some simulations, we create some models for the polyethylamide, this polymer, and we carried out some simulations to see what's going on. So here in what's colored different, it's just some species that are gonna meet at the end to form the structure. So we can follow all the trajectories and understand what are the most important steps toward starting for a linear polymer and getting at the end, I'm gonna jump to the final, structures that are more rigid, with pores of different size, with functional groups distributed, that match most of the experimental results. So we are now going further, trying to investigate all the steps that lead from polymer to the final membrane, computing what's the nature of the carbon atoms, the fraction of crystalline and amorphous carbon, what are the gases that are released, that's something that they can measure on the experiment. And now we're starting this month a project with Petrobras that's interested in developing these members for separation of olefins. So we got the project to develop both the experimental part and the computational part. We are very happy. It's a very challenging problem, and we have a lot of things to figure out. How do we do that using, of course, reacts? Other example, then I'll finish with reactive force fields. We have a lab at my university they call it high pressure. They like putting things under high pressure and see what happens. Anything you can imagine. And one case was graphite oxide. Usually when you reduce graphite oxide just by thermal annealing, you end up forming reduced graphene oxide that has a lot of defects. But they saw that if they applied high pressure, you degrade, but at the end you have very crystalline small domains, nanocrystals, graphite, graphene nanocrystals deposited on the surface. And they wanted to understand what's the difference between the process at ambient pressure and high pressure. So they have a lot of characterization results. So we could run simulations to see what happens. This is one example where we start with a sample of graphite oxide. Codec indisponível, it won't work the movie. That's okay. So we can compute the evolution of the structure over time under different pressures and see how much of the oxygen stays on the structure, how it diffuses along the material, what are the transformations that induce, and at the end you could figure out why at higher pressures you can get like cleaner regions of graphite, basically do a confinement effect. So the volume is lower, the molecules tend to stay at the surface, diffuse until they find defect, and they cut the sheets in smaller parts, leading to those small nanocrystals that we saw in the experiments. It's a very nice work. It was a PhD work, experimental work from physics, and a master's dissertation on the numerical aspect. So we had a lot of other things that I could show you, but I think I'm running out of time. So we can use these minutes to answer any questions you might have. So thank you very much. And thank you again for the invitation.